Have you ever gazed up at the night sky and felt that tug of wonder, that silent whisper pulling your imagination toward the stars? Out there, beyond the familiar glow of our own galaxy, lies a universe so vast and strange it defies everything we think we know. Picture this: cosmic structures so enormous they stretch the limits of physics, so mysterious they rewrite the rules of existence itself. These aren't just distant objects, they're cosmic riddles waiting to be unraveled, each one a chapter in a story far grander than we ever imagined. Today, we're setting out on a journey to explore 25 of the most enigmatic structures the universe has hidden from us, structures so baffling they challenge even our boldest scientific theories. From colossal walls of galaxies that shouldn't exist to voids so empty they feel like cosmic errors, these are the places where the universe seems to laugh at our understanding. What if I told you there's a structure so large it would take light billions of years just to cross it? Or that some cosmic formations appear to move in ways that defy gravity itself? These aren't science fiction, they're real, they're out there, and they're begging us to question everything. This isn't just about marveling at the unknown, it's about confronting the edges of human knowledge. Every one of these cosmic oddities holds a clue, a piece of the puzzle that could redefine how we see reality. And as we dive deeper, you'll start to feel it too, that thrilling ache of curiosity, the same one that drove the first astronomers to map the stars. So let's begin, because the universe isn't just waiting to be discovered. It's waiting to astonish us. Hidden in the depths of space, roughly 250 million light-years away, lurks a force so powerful it bends the very fabric of our universe, the Great Attractor. Picture an invisible hand tugging at thousands of galaxies, including our own Milky Way, pulling them toward a point in the constellation Centaurus at speeds exceeding 1.5 million miles per hour. Astronomers first noticed something strange in the 1970s when they mapped the motion of galaxies and realized they were all streaming toward this uncharted region like moths to a cosmic flame. But here's the twist: we can't actually see what's pulling them. The culprit lies behind what scientists call the zone of avoidance, a thick band of dust, gas, and stars from our own galaxy's disk that blocks our view of the universe beyond. It's like trying to peer through a fogged-up window while standing in a crowded room. Even our most powerful telescopes struggle to penetrate this celestial blind spot. What little we've glimpsed suggests the Great Attractor isn't just a single massive object, but an unimaginably dense knot of galaxies and dark matter, a gravitational anchor reshaping everything around it. And that's where the mystery deepens. The sheer scale of its influence hints at something even larger at play, perhaps a supercluster of galaxies so colossal it defies our models of cosmic structure. Some researchers believe this could be the heart of Laniakea, a vast galactic superhighway spanning 500 million light-years. Yet the Great Attractor's pull is stronger than what visible matter alone can explain, pointing again to the enigma of dark matter. Could this be a portal to understanding how invisible forces sculpt the universe? Or is it a sign that our theories of gravity need rewriting? Every answer we chase only leads to new questions, and that's what makes this cosmic phantom so irresistible. But if the Great Attractor represents a mysterious pull of gravity, its cosmic opposite might be even more unsettling, an expanse so empty it feels like the universe forgot to fill it in. Meet the Boötes Void, a spherical region of space spanning 330 million light-years where galaxies are almost shockingly absent. Astronomers call it the Great Nothing, and for good reason. While typical regions of the universe contain thousands of galaxies, the Boötes Void holds only 60 or so, a handful scattered in an incomprehensible ocean of darkness. To put that in perspective, if our Milky Way were placed in the center of this void, humanity wouldn't have discovered other galaxies until the 1960s because the nearest one would be too distant to see with early telescopes. So how did this cosmic dead zone come to exist? One theory points back to the primordial universe, where slight density fluctuations after the Big Bang might have left some regions stretched thin over time, like dough spreading until it's full of holes. Another idea suggests smaller voids merged, their combined emptiness snowballing into this staggering void. But there's a wilder possibility, one that taps into our fascination with the unknown. Some have speculated whether an advanced civilization could have engineered this emptiness, constructing hypothetical megastructures like Dyson spheres on an unimaginable scale, harvesting the energy of entire galaxies and leaving behind nothing. While there's no evidence to support this, the sheer scale of the Boötes Void forces us to ask, are we seeing a natural phenomenon or something beyond our current comprehension? What makes the Boötes Void particularly eerie is how it defies our expectations. The universe on large scales should look roughly the same everywhere, a principle called the cosmological principle. But this void is so vast and so empty that it challenges that assumption, making scientists wonder if our models of cosmic structure need revisiting. Even stranger, the few galaxies inside the void seem oddly isolated, like lone survivors in a wasteland. One of them, a dim spiral galaxy named MCG plus 053616, sits so alone that its nearest neighbor is millions of light-years away. Yet the Boötes Void isn't just a cosmic curiosity, it's a laboratory. By studying how light bends around its edges or how galaxies within it behave differently, astronomers might uncover secrets about dark energy, the mysterious force accelerating the universe's expansion. And if voids like this are more common than we thought, they could reshape our understanding of how the universe evolved. So while the great nothing might seem like emptiness incarnate, it's really a puzzle waiting to be solved, one that reminds us how much of the universe remains hidden in plain sight. Now let's shift our gaze to a structure so immense it makes the Boötes Void seem like a tiny pocket of nothingness, the Hercules-Corona Borealis Great Wall. Stretching an almost incomprehensible 10 billion light-years across, this cosmic filament isn't just large, it redefines the very meaning of scale. To put that in perspective, if you could travel at the speed of light, it would take you twice the age of Earth just to cross from one end to the other. This isn't just a collection of galaxies, it's a sprawling web of galactic superclusters, a backbone of the universe woven from threads of dark matter and starlight. What's truly staggering isn't just its size, but the fact that it exists at all. For decades, scientists operated under the cosmological principle, the idea that, on large enough scales, the universe should look roughly the same no matter where you are. But the Hercules-Corona Borealis Great Wall shatters that assumption. Picture tossing a handful of sand onto a table and expecting it to spread evenly, only to find it clumped into a single towering ridge. That's essentially what this structure does to our models of cosmic evolution. Its sheer scale suggests a level of clustering that shouldn't have had enough time to form after the Big Bang, raising urgent questions about how such a colossal assembly could emerge in just 13.8 billion years. The discovery came as a shock in 2013, when astronomers analyzing gamma-ray bursts, the brightest explosions in the universe, realized they were tracing the outlines of something far grander. These bursts acted like cosmic breadcrumbs, revealing a structure so vast it spans a tenth of the observable universe. And here's where things get even stranger. The wall isn't just a flat sheet. It's a three-dimensional labyrinth with galaxies and clusters tangled like knots in a net, defying our expectations of how matter should distribute itself across the cosmos. But the real puzzle lies in the math. According to our current understanding of cosmic inflation, the rapid expansion of the universe right after the Big Bang, structures this enormous simply shouldn't have had the time to gravitationally bind together. Some theories suggest the answer might lie in exotic physics, like primordial energy fields that left behind imprints of uneven density. Others speculate that this could be evidence of a multiverse, where the wall marks the boundary of a bubble universe colliding with our own. Whatever the explanation, one thing is clear. The Hercules-Corona Borealis Great Wall isn't just a structure, it's a challenge, a cosmic anomaly forcing us to rethink the fundamental rules of reality. Yet for all its mystery, the wall also offers a glimpse of hope. By studying its gravitational influence, the way it bends light around its edges, or even the peculiar motions of galaxies within it, astronomers might uncover clues about dark energy and the universe's ultimate fate. Because if there's one lesson this titanic structure teaches us, it's that the universe loves to surprise us, and the biggest revelations often come from the places we least expect. Just when we thought the universe couldn't get any stranger, astronomers stumbled upon something that defies logic, a celestial curve so vast it rewrites the rules of cosmic architecture. Meet the giant arc, a sprawling crescent of galaxies stretching a mind-bending 3.3 billion light-years across the northern sky. Discovered in 2021 by a team analyzing the light of distant quasars, this structure isn't just big, it's a brazen challenge to everything we thought we knew about how the universe organizes itself. Imagine drawing a rainbow across the night sky, but instead of colors, it's made of galaxy clusters, hydrogen clouds, and dark matter, all bending through space like a cosmic eyebrow raised in defiance. What makes the giant arc so revolutionary isn't just its size, though that alone is staggering, but its very existence. According to our best models of cosmic evolution, matter should distribute itself relatively evenly across the universe on scales larger than 1.2 billion light-years. Yet here we have a structure nearly 3 times that limit, its galaxies aligned in a graceful curve that seems to whisper, "Your math is missing something." It's as if you tossed a handful of pebbles into a pond, and instead of scattering randomly, they arranged themselves into a perfect circle. The giant arc forces us to confront an uncomfortable truth. Either our understanding of the universe's infancy is flawed, or there's a physics we haven't yet uncovered guiding these colossal patterns. The discovery hinged on a clever trick of observation. By mapping the glow of magnesium ions in distant quasars' ultra-bright galactic cores, astronomers traced an invisible scaffold of gas linking dozens of galaxy clusters. These clusters aren't just neighbors, they move in concert, bound by gravity in a dance that spans billions of years. But here's where it gets even weirder: the giant arc isn't alone. It shares the sky with other enormous structures like the Hercules-Corona Borealis Great Wall, suggesting the universe might favor these vast, filamentous designs more than we ever anticipated. Some researchers speculate these could be echoes of quantum fluctuations from the Big Bang itself, frozen in time and stretched to unimaginable scales by cosmic inflation. Yet not everyone is convinced. Skeptics argue the giant arc might be a trick of perspective galaxies that only appear connected from our vantage point but are actually scattered at different depths. But counter-studies show the alignment holds even when accounting for 3-dimensional space, deepening the mystery. If confirmed, this structure could upend the cosmological principle entirely, hinting that the universe isn't as uniform as we believed. Perhaps most tantalizing is what the giant arc implies about dark matter. Its gravitational grip seems to sculpt the curve, weaving galaxies into this improbable shape. Could this be a clue to dark matter's true nature, or even evidence of its uneven distribution? Every new observation pulls us deeper into the enigma, proving once again that the universe reserves its most audacious surprises for those willing to look beyond the expected. Among the universe's countless galaxies, few are as visually striking or as baffling as Hoag's object. Picture a perfect cosmic bullseye, a luminous yellow core encircled by a pristine ring of blue stars, separated by a dark, seemingly empty gap. Discovered in 1950 by astronomer Art Hoag, this peculiar galaxy floats 300 million light-years away in the constellation Serpens, defying nearly every expectation of how galaxies should look. Most galaxies, like our Milky Way, spiral with elegant arms or take the form of fuzzy ellipses. But Hoag's object, it's a celestial oddity, a cosmic donut so symmetrical it feels engineered rather than born from chaos. So how does something so perfectly circular come to exist? The leading theory points to a violent past, a galactic collision so precise it's almost poetic. Imagine two galaxies, one young and rich with gas, the other older and denser, passing through each other like ghosts. The gravitational shock waves from their encounter could have sent ripples through the gas clouds of the larger galaxy, compressing them into a ring where new stars ignite in a brilliant blue halo. Meanwhile, the original core remains undisturbed, leaving that glowing golden center. It's a rare and delicate dance, one that requires just the right angle, speed, and mass to create this pristine structure instead of a mangled wreck. But here's the twist. Hoag's object shows no signs of a recent collision. No debris, no twisted trails of stars, just eerie silence where evidence should be. This has led to alternative theories like density waves resonating through the galaxy's gas, or even the slow accretion of intergalactic material sculpted by an ancient black hole's influence. Some researchers speculate it could be an extreme example of a barred galaxy where the bar dissolved over time, leaving only the ring behind. What makes Hoag's object even more fascinating is its rarity. Despite decades of searching, astronomers have found fewer than 20 galaxies with similar structures, leading some to call them Hoag-type galaxies. Each one is a cosmic puzzle, challenging our assumptions about galactic evolution, and the mysteries don't end there. Recent observations reveal that Hoag's object might not be alone inside its dark gap. There's a faint, separate ring of stars, hinting at an even more complex history. Could this be evidence of multiple collisions or something else entirely? Standing as both a work of art and a scientific enigma, Hoag's object reminds us that the universe has a flair for the unexpected. Its existence pushes us to rethink how galaxies form and evolve, proving that even the most familiar cosmic phenomena can hide astonishing secrets, and perhaps the most thrilling part. Every unanswered question it raises is an invitation to look deeper, to question further, because the truth is out there, waiting in the darkness between the stars. Among the universe's most perplexing mysteries is a motion so subtle yet so vast it threatens to rewrite our cosmic playbook. The dark flow. Imagine countless galaxy clusters, each weighing trillions of suns, drifting like leaves caught in a celestial current, all pulled toward a distant point beyond the edge of the observable universe. This isn't just random motion, it's a coordinated march, a flow so persistent that it defies the uniform expansion we've long attributed to the cosmos. Discovered in 2008 by analyzing the peculiar velocities of galaxy clusters in the cosmic microwave background, the dark flow suggests something immense and invisible is tugging at the fabric of reality itself. The numbers alone are staggering. These clusters are racing toward the constellations Centaurus and Hydra at speeds exceeding 800 kilometers per second, far faster than standard models of cosmic expansion can explain. What's even stranger, this motion isn't caused by the gravitational pull of anything we can see. No known supercluster, no concentration of dark matter, no observable structure in the universe has enough mass to orchestrate such a synchronized movement. It's as if the universe has a hidden hand, one that reaches beyond the limits of our telescopes. So what could be driving this enigmatic current? One tantalizing theory points to the gravitational influence of a supermassive structure lurking just outside our observable bubble. Perhaps a colossal concentration of matter left over from the inflationary epoch, a relic so ancient it predates the cosmic microwave background itself. Others propose something even more radical. The dark flow might be evidence of a neighboring universe, its gravity leaking into ours through the fabric of space-time. Picture two soap bubbles pressed lightly together. Where they meet, their membranes might subtly interact. If true, this could be our first indirect glimpse of the multiverse, a shadowy realm exerting its pull from beyond the cosmic horizon. But not all scientists are convinced. Skeptics argue the dark flow could be an artifact of measurement errors or incomplete data, a cosmic mirage born from the challenges of mapping such vast distances. Some suggest alternative explanations, like large-scale inhomogeneities in the universe's density regions where matter clumped unevenly during the Big Bang, creating gravitational tides that still ripple through space today. Yet the dark flow persists in defying easy dismissal. Follow-up studies using newer datasets like those from the Planck satellite have both supported and contradicted the phenomenon, leaving the debate wide open. What's undeniable is how this mystery forces us to confront the limits of our knowledge. If the flow is real, it hints at a cosmos far larger and more interconnected than we ever imagined, one where unseen forces sculpt the universe on scales beyond comprehension. Perhaps the most thrilling aspect of the dark flow isn't just the question of what's causing it, but what it means for our understanding of reality. Could this be the thread that unravels the cosmological principle, proving the universe isn't uniform after all? Or might it reveal new physics, a gravitational anomaly woven into the fabric of spacetime itself? Every observation, every recalibration of our instruments brings us closer to answers or deeper into the unknown. And that's the beauty of cosmic mysteries. They don't just challenge our theories, they invite us to dream bigger. Imagine an ancient cosmic fog glowing with the light of newborn stars, but on a scale so vast it could swallow entire galaxies. This is the eerie beauty of Lyman alpha blobs, some of the largest and most enigmatic structures in the early universe. These colossal clouds of hydrogen gas stretch hundreds of thousands of light-years across, radiating a ghostly ultraviolet glow known as Lyman alpha emission. First discovered in the late 1990s, these blobs serve as cosmic time capsules, offering us a glimpse into an era when the universe was still in its turbulent adolescence. What makes these blobs so fascinating isn't just their size, it's the mystery of what powers them. Normally, hydrogen gas only glows this brightly when it's energized by something extreme. The furious birth of stars, the ferocious winds of supermassive black holes, or even the shockwaves from colliding galaxies. Yet some Lyman alpha blobs float in relative isolation, their light-defying easy explanation. Picture a neon sign in the middle of a desert, glowing without any visible power source. That's the puzzle astronomers face. How can these clouds shine so intensely without the usual cosmic engines nearby? One leading theory points to quasars, the brilliant cores of distant galaxies where supermassive black holes feast on surrounding matter. The intense radiation from these monsters could illuminate hydrogen clouds far beyond their own galactic borders, like a lighthouse beam cutting through fog. Another idea suggests these blobs might be cosmic nurseries, where streams of cold gas collapse under gravity, igniting waves of star formation so dense they light up the entire cloud. But there's a twist. Some blobs show no signs of stars or black holes at all, leaving researchers to wonder if we're seeing the fingerprints of dark matter, its gravitational pull somehow heating the gas to a luminous glow. The most compelling clue lies in their age. Lyman alpha blobs are relics of a time when the universe was just 2 or 3 billion years old, an epoch when galaxies were still assembling themselves. These blobs could be the scaffolding of the cosmos, the hidden infrastructure where gas funneled into the earliest galactic hubs. Computer simulations suggest that without these vast reservoirs of hydrogen, modern galaxies like our Milky Way might never have formed. They're the invisible architects of the cosmic web, their glow a fleeting beacon from an era before stars lit up the darkness. Yet for all their importance, Lyman alpha blobs remain frustratingly elusive. Their light is so faint and red-shifted by the expansion of the universe that only the most powerful telescopes can detect them. Even then, they appear as hazy smudges, their secrets locked in wavelengths just beyond our reach. But with next-generation observatories like the James Webb Space Telescope peeling back the layers of time, we might soon uncover what makes these cosmic ghosts burn so brightly. And when we do, it could rewrite the story of how galaxies and everything in them came to be. The beauty of these blobs lies not just in their mystery, but in what they represent, a universe still wild and untamed, where the rules we take for granted bend and break. They remind us that even in the darkest corners of space, light finds a way, and so does our curiosity. Deep in the cosmic microwave background, the afterglow of the Big Bang itself, there's a patch of sky that doesn't belong. Dubbed the cold spot, this mysterious region glows 70 microkelvin cooler than its surroundings, stretching over 1.8 billion light-years in the constellation Eridanus. At first glance, it might seem like a minor imperfection in the universe's oldest light, but this anomaly is anything but ordinary. It's a cosmic bruise, a shadow on the fabric of reality that has astronomers locked in a heated debate. Is it the imprint of a collision with another universe, or just a gaping void in our own? The cold spot first made waves in 2004, when NASA Wilkinson Microwave Anisotropy Probe mapped the cosmic microwave background with unprecedented precision. The data revealed subtle temperature fluctuations, most of which fit neatly into our models of cosmic evolution. But this spot, it stood out like a frozen thumbprint, too large and too cold to be mere statistical noise. Follow-up observations only deepened the mystery. The European Space Agency's Planck satellite confirmed its existence, ruling out instrument errors or data glitches. This was real, and it demanded an explanation. One camp argues the cold spot is a supervoid, an enormous, underdense region of space where the lack of galaxies and matter subtly cools the cosmic microwave background as light passes through. It's a well-documented phenomenon known as the integrated Sachs-Wolf effect. Photons lose energy climbing out of a void's weakened gravitational pull, shifting their light toward cooler temperatures. But here's the catch: for a void to explain the cold spot's extreme chill, it would need to be so vast and empty that it defies our understanding of large-scale structure. Simulations suggest such a void should be nearly impossible in our current cosmological framework, like finding a desert the size of a continent where none should exist. That's where the wilder theories come in. Some physicists propose the cold spot is evidence of a cosmic collision, a bruise left behind when our universe grazed another in the multiverse. Picture two soap bubbles bumping in a froth of universes, their membranes briefly touching. The energy transfer at that boundary could have created a localized cold zone in our cosmic microwave background, a relic of that unimaginable encounter. It's a radical idea, but not without precedent. Theories like eternal inflation suggest the multiverse should be filled with bubble universes, and occasionally those bubbles might interact. Yet the cold spot refuses to yield easy answers. Even the supervoid hypothesis has its skeptics. Recent galaxy surveys found a large underdense region near the cold spot, but its size and emptiness don't quite match what's needed to fully explain the temperature drop. This leaves room for more exotic possibilities, like textures, topological defects in space-time, left over from the universe's early symmetry-breaking phases. These cosmic knots, if they exist, could create localized distortions in the cosmic microwave background, leaving behind cold imprints like the one we're seeing. What makes the cold spot so compelling isn't just the battle between mundane and exotic explanations, it's the way it forces us to test the limits of our knowledge. If it's a void, then our models of cosmic structure need serious revision. If it's a multiverse signature, then we're staring at the first tangible evidence of realities beyond our own. And if it's something else entirely, well, that's the thrill of cosmic discovery. Every anomaly, every outlier is a crack in the facade of our understanding, one that might just lead us to a deeper truth. For now, the cold spot remains an open case, a cosmic cold file waiting for the next breakthrough. Future telescopes, like the Euclid Space Observatory, could map the distribution of galaxies and dark matter in unprecedented detail, shedding light on whether the void hypothesis holds water. Meanwhile, theorists continue to refine their multiverse models, searching for testable predictions. Whatever the answer turns out to be, one thing is certain: the universe loves to keep us guessing. And in that uncertainty, science finds its most exciting questions. Rising like twin titans from the heart of our galaxy, the Fermi Bubbles defy everything we thought we knew about the Milky Way's quiet middle age. These colossal structures, each stretching 25,000 light-years from the galactic center, glow with an eerie gamma-ray light, a silent testament to some cataclysmic event that shook our cosmic neighborhood. Discovered in 2010 by NASA, a Fermi gamma-ray space telescope, these bubbles aren't just large, they're violent. Their edges crackle with high-energy radiation, as if the galaxy itself exhaled a scream into the void. What could unleash such fury? The leading suspect is Sagittarius, a star, the supermassive black hole lurking at our galaxy's core. Astronomers theorize that millions of years ago, this sleeping giant might have awoken in a feeding frenzy, devouring stars or gas clouds with such ferocity that it blasted jets of energized particles straight up and down the galactic plane. Imagine a volcano erupting not with lava, but with pure radiation sculpting these vast bubbles like cosmic smoke rings. The energy required staggers the mind. Each bubble pumps out the equivalent of 100,000 supernova, a testament to the raw power of black holes when they stir. But there's a twist. Not all scientists are convinced this was a black hole tantrum. Some propose an even more exotic explanation: dark matter annihilation. If certain theoretical particles of dark matter collide and annihilate near the galactic center, they could release bursts of gamma rays, potentially inflating these bubbles like balloons. It's a tantalizing idea because, if true, the Fermi bubbles might be our first visible clue to dark matter's elusive nature. Yet the puzzle deepens when we study the bubble's structure. Their sharp edges and symmetrical shapes suggest a sudden, violent injection of energy rather than a slow leakage, something more like a single explosive event than a steady process. Adding to the mystery are the so-called E-Rosetta bubbles detected in 2020 by an X-ray telescope. These even larger structures overlap with the Fermi bubbles but glow in softer X-rays, hinting at multiple epochs of activity, like layers of paint on a cosmic canvas. Could this mean our galaxy's center erupts cyclically, with each outburst leaving its mark? Or is there a more complex interplay between black hole physics and dark matter at work? The Fermi bubbles force us to confront how little we know about our own galactic home. They remind us that even apparently quiet galaxies like the Milky Way have violent pasts, and that the universe loves to hide its most explosive secrets in plain sight. Every new observation peels back another layer, bringing us closer to understanding what really happened at the heart of our galaxy and what might happen again. If walls could talk, the Sloan Great Wall would roar, a staggering filament of galaxies stretching 1.4 billion light-years across the cosmos, a structure so immense it dwarfs even the most audacious cosmic blueprints. Discovered in 2003 by the Sloan Digital Sky Survey, this labyrinth of superclusters and voids isn't just a curiosity. It's a cosmic rebellion, defying our assumptions about how matter should distribute itself in the universe. Picture a spider's web spun on a galactic scale, its threads woven from thousands of galaxies bound by gravity, except this web is larger than any single structure should theoretically be. What makes the Sloan Great Wall so unsettling to astronomers isn't just its size, though that alone is mind-bending, but how it mocks the cosmological principle, the idea that the universe should look roughly the same everywhere at large scales. Imagine stirring cream into coffee, and instead of blending evenly, it forms a single thread stretching from rim to rim. That's the Sloan Wall's defiance. It's a thread of matter so dense and elongated that it challenges the notion of cosmic uniformity. Yet it's not alone. Other titanic walls like the Hercules-Corona Borealis Great Wall or the CFA2 Wall, echo this pattern, suggesting the universe might prefer weaving these colossal tapestries over scattering matter randomly. The strangest part, we don't fully understand how such giants could form so quickly after the Big Bang. According to our best models, gravity needs time to pull matter into structures this vast, more time, perhaps, than the 13.8 billion years the universe has existed. One theory points to dark matter's invisible scaffolding, its gravitational pull accelerating the growth of these filaments. Another wild idea involves quantum fluctuations in the early universe, those microscopic wrinkles in space-time that inflation stretched to cosmic proportions, leaving behind blueprints for these walls. But the Sloan Great Wall isn't just a theoretical headache. It's also a cosmic time capsule. By studying the types of galaxies within it, their ages and motions, astronomers can trace how matter evolved over billions of years. Some regions resemble modern galaxy clusters, while others seem frozen in the universe's youth, their stars barely matured. This patchwork hints at an even deeper mystery. Why do some parts of the wall look ancient while others appear newborn? Is this a clue to uneven cosmic expansion or evidence of dark energy's fickle influence? Standing in the shadow of this titan, we're left with more questions than answers. Does its existence demand a rewrite of cosmology's rulebook, or are we simply seeing the limits of our current tools? Future telescopes like the Vera C. Rubin Observatory might reveal whether the Sloan Wall is truly unique or just one thread in an even grander design. Either way, its sheer audacity reminds us that the universe has a flair for the dramatic and a knack for keeping us humble. At the heart of the Phoenix cluster, a monstrous gravitational beast defies every expectation, a black hole so massive it tips the scales at 20 billion times the weight of our Sun. This isn't just a cosmic vacuum, it's a paradox, a singularity that shouldn't exist according to the rules we thought governed black hole growth. The Eddington limit, a theoretical ceiling for how fast a black hole can devour matter, crumbles in its presence, leaving astronomers scrambling to explain how this leviathan grew so large so fast. What makes this black hole truly exceptional isn't just its size, but its appetite. Most supermassive black holes are thought to feed in fits and starts, their growth limited by the very radiation they produce as they consume gas and stars. The energy released during these meals pushes surrounding material away, effectively putting the brakes on further feasting. But the Phoenix cluster's black hole behaves more like a cosmic glutton, slurping down matter at rates that should be impossible. Imagine trying to drink from a fire hose while the water vaporizes before it reaches your mouth, yet somehow, this black hole keeps swallowing. The key to its defiance might lie in the environment around it. The Phoenix cluster is a sprawling metropolis of galaxies swimming in a superheated sea of gas known as the intracluster medium. Normally, this gas should be too diffuse and energetic for any black hole to dominate. But here, the central black hole isn't just a passive resident, it's an architect sculpting its surroundings with terrifying efficiency. Jets of plasma blast from its poles at near light speed, carving vast cavities in the intracluster medium while shock waves ripple outward like cosmic tsunamis. These eruptions should stifle further growth, yet somehow fresh gas keeps funneling toward the black hole's maw. One radical theory suggests the answer lies in chaotic accretion, a messy, turbulent feeding process where gas doesn't spiral in neatly but crashes inward in clumps and streams, bypassing the Eddington limit's restrictions. Picture trying to fill a bucket during a hurricane. While most rain gets blown sideways, enough still falls in to overwhelm the container. Alternatively, the black hole might be tapping into hidden reservoirs of cold gas, filaments of material threading through the cluster like unseen rivers feeding a hidden ocean. But the implications stretch far beyond this single black hole. Its existence hints that our understanding of cosmic ecosystems, how galaxies and clusters evolve, might be missing a crucial piece. If black holes can grow this massive, this quickly, they could dominate their environment sooner than we thought, shutting down star formation across entire galaxies by overheating surrounding gas. The Phoenix Cluster's black hole isn't just a curiosity. It's a warning that the universe's most extreme objects might operate by rules we're only beginning to glimpse. And then there's the timescale problem. To reach 20 billion solar masses, this black hole would need to consume staggering amounts of matter almost continuously since the dawn of the universe. Yet the Phoenix Cluster itself isn't ancient, it's a relatively modern structure. This raises a spine-tingling question. Could there be mechanisms for black hole growth we haven't even dreamed of? Some theorists whisper about primordial black holes born in the chaos of the Big Bang, seeding the cosmos with ready-made giants. Others wonder if dark matter, mysterious and invisible, might somehow fuel these behemoths in ways we can't yet detect. What's certain is that this black hole refuses to fit neatly into our models. It's a cosmic outlier, a challenge carved into the fabric of space itself. Every observation peels back another layer of mystery, reminding us that the universe's most awe-inspiring spectacles often lurk where our theories fall silent. Floating in the constellation Monoceros like a celestial stained glass window, the Red Rectangle Nebula defies every expectation of what dying stars should leave behind. At its heart lies HD 44179, a binary star system nearing the end of its life, yet instead of the chaotic, asymmetrical clouds typical of stellar death, this nebula erupts in near-perfect geometric splendor. Its sharp X-shaped beams and layered rectangular rungs glow with an eerie red hue, a structure so precise it looks almost engineered. How does nature sculpt such mathematical perfection from the chaos of stellar winds? The secret might lie in the dance of the central stars. Most planetary nebulae form when a single dying star sheds its outer layers, creating billowing waves of gas and dust. But HD 44179 isn't alone. It's locked in orbit with a companion star, their gravitational waltz shaping the outflow into something extraordinary. As the primary star expels material, the secondary star's gravity funnels it into two opposing cones, like squeezing toothpaste from both ends of the tube. These cones collide with a disk of dust encircling the system, sculpting the ejected gas into those unmistakable X-shaped spikes. Meanwhile, the rectangle's rungs may be shockwaves, ripples in the outflow where faster-moving material crashes into slower streams, creating stacked, luminous shelves. But here's where the mystery deepens. The red rectangle's symmetry is almost too perfect. Observations reveal the X structure isn't just a rough outline. It's precise down to startlingly straight lines with angles that suggest intricate physics at play. Some researchers propose magnetic fields, invisible threads woven through the nebula, might be guiding the outflow into these razor-sharp forms. Others point to the unique chemistry of the system. The nebula's red glow comes not just from hydrogen but from complex carbon molecules called polycyclic aromatic hydrocarbons which thrive in the dense dust lanes. These molecules, rarely seen in such abundance around dying stars, hint at a cosmic alchemy we're only beginning to understand. Even more intriguing are the nested rectangles themselves. Unlike most nebulae where structures blur into haze, the red rectangle's rungs appear evenly spaced, like tree rings recording stellar history. One theory suggests they're caused by periodic bursts of mass loss from the central star, ejecting material in pulses that froze into these luminous steps. If true, each layer could mark a distinct chapter in the star's death, throws a timeline written in light and gas. Yet for all its beauty, the red rectangle is ephemeral. In a few thousand years, a blink in cosmic time, its delicate structures will dissipate, leaving only a fading white dwarf behind. That fleeting nature makes it all the more precious, a glimpse into the brief, brilliant moment when gravity, motion, and chemistry conspire to create something sublime. And perhaps its greatest lesson isn't just how stars die, but how even in their final act, they can paint the cosmos with geometry worthy of a master artist. Hovering over Saturn's north pole like a colossal geometric guardian, the hexagon is one of the solar system's most hypnotic mysteries, a 30,000-kilometer-wide storm so precise it looks etched into the sky by an unseen hand. Unlike the chaotic swirls of Jupiter's great red spot or Earth's ever-shifting hurricanes, this six-sided vortex has remained eerily stable for at least 4 decades, possibly centuries. Its walls tower 100 kilometers high, with winds screaming at 320 kilometers per hour, yet the structure itself rotates with the mechanical precision of a celestial gear. How does a planet known for its graceful rings produce something so unnervingly angular? The hexagon's strangeness only deepens when we compare it to Earth's polar vortices. Our planet's polar winds twist and buckle with the seasons, breaking apart and reforming like temporary atmospheric knots. But Saturn's hexagon is locked in place, its 6 sides maintaining near-perfect symmetry even as hurricanes spin inside its borders. The key difference might lie in what scientists call atmospheric waveguide standing waves, resonant vibrations that shape fluid motion like sound waves shaping music. Picture blowing across the top of a soda bottle. The pitch depends on the bottle's size and shape. Saturn's hexagon could work similarly with the planet's rapid rotation. A day lasts just 10.5 hours, and deep atmosphere creating a natural waveguide that sings at a frequency producing this geometric pattern. Yet not all researchers are convinced. Alternative theories suggest the hexagon might be a colossal version of something we see in lab experiments. When fluids of different densities rotate at varying speeds, they sometimes form polygonal shapes. Saturn's layered atmosphere, with its bands moving at different velocities, could naturally give rise to such structures. Others propose the hexagon is a towering stack of smaller vortices, their combined motion sculpting the edges into straight lines through sheer momentum. Then there's the wild card, Saturn's magnetic field, which might interact with charged particles in the atmosphere to stabilize the storm's edges like an invisible mold. What makes the hexagon truly tantalizing is what it reveals about planetary atmospheres as cosmic laboratories. Earth's weather operates on relatively small scales, governed by surface friction and water cycles. But Saturn's atmosphere is a hydrogen-helium sea hundreds of kilometers deep, where traditional weather rules don't apply. Studying the hexagon could unlock secrets about how energy moves in fluid systems across the universe, from the swirling depths of gas giants to the plasma currents of distant stars. And perhaps most strikingly, it reminds us that nature's love of geometry isn't confined to crystals or honeycombs. Even in the maelstrom of a planetary storm, the universe finds a way to paint with straight edges. As Cassini's final images of the hexagon showed before the probe's deliberate plunge into Saturn's atmosphere, the structure persists even as seasons change on the ringed planet. Unlike Earth's poles, where warming temperatures can disrupt vortices, Saturn's hexagon endures, a testament to the delicate balance of forces governing alien skies. Whether it's a resonant song written in wind, a dance of competing storms, or something even stranger, one thing is clear: this isn't just a weather pattern. It's a cosmic sculpture, and we're only beginning to trace its chisel marks. On the sweltering night of August 15, 1977, a radio telescope in Ohio captured something extraordinary, a signal so powerful and peculiar that an astronomer scribbled, "Wow," in the margins of the data printout, giving birth to one of space's most tantalizing mysteries. For 72 seconds, the Big Ear radio telescope recorded a narrowband burst at 1420 MHz, a frequency where hydrogen naturally emits energy, and one considered ideal for interstellar communication. Then, just as suddenly as it appeared, the signal vanished, leaving behind decades of speculation and an enduring question: was this a cosmic hello, or simply nature playing a trick on us? The WOW signal's allure lies in its perfect artificial profile. Unlike the static hiss of cosmic noise or the erratic pulses of quasars, This burst was clean, concentrated, and seemingly engineered, exactly what scientists predicted an extraterrestrial transmission might look like. It came from the direction of the constellation Sagittarius, near the star Chi Sagittarii, a region scanned repeatedly since without success. Modern SETI projects, armed with sophisticated algorithms and telescope arrays, have turned their gaze toward this patch of sky, hunting for echoes of that enigmatic blast. Yet despite decades of listening, the silence remains unbroken, deepening the puzzle. One leading natural explanation points to hydrogen clouds around comets. In 2016, astronomer Antonio Paris proposed that two previously undiscovered comets, 266P and 335P, might have been passing through that region, their icy nuclei releasing hydrogen plumes that could mimic an artificial signal. While intriguing, this theory has holes. The comets weren't in the telescope's field of view at the exact time of the detection, and later searches for similar signals from other comets came up empty. The signal's intensity also far exceeds what cometary hydrogen should produce, leaving many unconvinced. Another camp argues for a terrestrial origin, a passing satellite or reflected radio signal bouncing off space debris. But the Big Ear's dual beam design makes this unlikely. The telescope used two feed horns scanning the sky minutes apart. A local signal would have appeared in both, while the WOW signal showed up in only one. That precision points to a celestial source, something beyond Earth's orbit. Then there's the possibility we dare not ignore, that for 72 seconds we intercepted something not just alien but intentional. The signal's frequency was within the water hole, a quiet band of the radio spectrum between hydrogen and hydroxyl lines, a logical place for civilizations to broadcast, as these molecules are essential to life as we know it. Its strength suggests a transmitter far more powerful than anything humanity has built, possibly a targeted beacon or an accidental leakage from some distant technology. Recent advances add new wrinkles to the mystery. Breakthrough Listen, the most comprehensive SETI initiative to date, has analyzed millions of radio signals since 2016, using machine learning to filter out interference. While they've found intriguing candidates, none match the WOW signal's purity. Meanwhile, astronomers have scanned the original coordinates with instruments like the Very Large Array, capable of pinpointing sources with arcsecond precision. Still, the sky stays silent, a reminder that in the vast cosmic ocean, signals might be rare, fleeting, or deliberately brief. What lingers isn't just scientific curiosity, but the weight of that single exclamation, "Wow." Scrawled in red ink, it captures the visceral thrill of confronting something inexplicable, a moment when the universe seemed to whisper directly to us. Whether the signal was a comet's cry, a glitch, or something far more profound, its legacy endures, a beacon not just of radio waves but of wonder, urging us to keep listening. Because out there in the dark, among the hydrogen and the silence, another signal might be waiting, one we won't have to question when we hear it. Some call it the most unsettling shadow in the afterglow of creation, an eerie alignment in the cosmic microwave background so improbable it earned the apocalyptic nickname, the Axis of Evil. This isn't some supernatural prophecy, but a cold statistical reality. When scientists mapped the faint temperature fluctuations in the universe's oldest light, they discovered an unexpected pattern, a mysterious axis where hot and cold spots seemed to align across vast swaths of the sky, as if the cosmos itself were subtly tilted. The discovery first surfaced in 2005, when cosmologists analyzing data from NASA's Wilkinson microwave anisotropy probe noticed something that made their equations itch. According to the standard cosmological model, the cosmic microwave background should resemble a random scattering of temperature variations like static on an old television set. Instead, the fluctuations showed a peculiar preference, clustering along an invisible line stretching between the constellations Leo and Aquarius. Even stranger, This axis appears loosely aligned with our solar system's ecliptic plane, the flat disk where planets orbit the Sun. The odds of such an alignment happening by pure chance. Less than 1 in 1,000. Dive deeper and the implications become staggering. If this axis reflects a genuine cosmic asymmetry rather than a measurement fluke, it could mean one of two terrifying possibilities. Either the universe has a preferred direction violating the foundational cosmological principle that insists space should look the same in all directions, or we're seeing contamination from something much closer to home. Imagine peeling an onion only to realize the layers were arranged to spell your name. That's the level of cognitive dissonance the axis of evil introduces to cosmology. Skeptics argue this might be an illusion, an artifact of foreground interference from our own galactic neighborhood. Dust clouds in the Milky Way, the Sun's motion through space, or even residual radiation from the solar system's infancy could potentially imprint false patterns on the cosmic microwave background. Some researchers have proposed that the axis is really just a ghost in the data, a consequence of how we process the microwave sky. Yet after nearly 2 decades of scrutiny with increasingly sensitive instruments like the Planck satellite, the anomaly stubbornly persists, resisting every attempt to explain it away. Then there's the radical interpretation. What if the axis of evil is real? Some theorists suggest it could be evidence of a pre-Big Bang structure, a cosmic fingerprint from an earlier universe that somehow imprinted itself on ours. Others float the idea of a dark flow scenario, where the gravitational tug of a neighboring universe beyond our observable horizon subtly warps the cosmic microwave background. The most mind-bending hypothesis, that we're seeing the first hints of spacetime being fundamentally anisotropic, stretched differently in certain directions due to quantum fluctuations frozen into the fabric of reality during inflation. What makes this debate so electrifying is what's at stake. If the axis proves genuine, it wouldn't just tweak our models, it would force a rewrite of cosmology's core rulebook. The cosmological principle isn't just academic philosophy, it's the bedrock upon which we've built our understanding of cosmic expansion, dark energy, and the universe's ultimate fate. Challenging it would be like discovering the Earth isn't round after all, but shaped like a cosmic pretzel. Yet for all its controversy, the axis of evil serves a crucial purpose. It keeps science honest. True progress often begins with anomalies that refuse to fit neatly into textbooks. Whether this peculiar alignment eventually topples paradigms or fades into obscurity, it reminds us that the universe owes us no obligation to make sense. And somewhere in that tension between expectation and observation, between the pristine theories and the messy reality, lies the thrilling frontier where discovery waits. Imagine a world where rain isn't water but liquid diamond, where continents glitter with crystallized carbon, and the very ground beneath your feet is forged under pressures so extreme it transforms into something celestial. This isn't science fiction, it's PSR J1719-1438b, a planet so dense and dazzling it defies the limits of planetary science. Orbiting a pulsar 2,300 light-years away in the constellation Serpens, this cosmic jewel began its life not as a planet at all, but as the heart of a dead star. The story of this diamond world begins with a stellar catastrophe. The pulsar it orbits, a rapidly spinning neutron star named PSR J1719-1438, wasn't always alone. Once it had a companion, a white dwarf, the smoldering core of a sun-like star. Over eons, the pulsar's gravity siphoned material from its neighbor, stripping the white dwarf down to a fraction of its mass. But here's where physics takes a surreal turn. Under the pulsar's relentless pull, the white dwarf didn't just fade, it collapsed into something entirely new. Crushed by pressures 1,000,000 times greater than Earth's core, the carbon-rich remnant crystallized, transforming into a planet-sized diamond orbiting its destroyer. What makes this world truly staggering isn't just its composition, but its defiance of categories. with a mass slightly greater than Jupiter crammed into a sphere just half as wide. PSR J1719-1438b is so dense a teaspoon of its material would weigh billions of tons on Earth. Its carbon lattice isn't like the gemstones we know. It's a hyper-compressed crystalline structure forged in conditions no laboratory could replicate. Some theorists speculate its interior might harbor even stranger phases of matter, like metallic hydrogen or degenerate electron fluids, blurring the line between planet and stellar remnant. Yet the diamond planet isn't just a cosmic curiosity, it's a window into stellar alchemy. Most carbon-rich worlds we've discovered are gas giants or icy bodies. This one represents a third path, a relic of stellar cannibalism frozen into permanence. Its existence suggests that pulsar planets, once thought to be rare accidents, might be more common than we imagined. After all, if a dying star can be sculpted into a diamond, what other impossible worlds lurk in the pulsar shadows? And then there's the light show. The pulsar itself spins over 10,000 times a minute, blasting its diamond companion with radiation and stellar winds. Under that onslaught, the planet's surface might glow with auroras unlike anything in our solar system, charged particles dancing across a crust of crystalline carbon, painting the darkness with spectral fire. It's a reminder that even in death, the universe finds ways to dazzle. But perhaps the most haunting question isn't how this world formed, but what it tells us about endings. The diamond planet is a tombstone, the last relic of a star that once shone as brightly as our sun. In its frozen beauty, we see the destiny of all carbon-rich systems, a hint that even Earth, with its organic riches, might one day face a similar transformation. After all, the elements that make up our bodies were forged in stellar furnaces. In a way, we're all just stardust waiting to become something new. And if the universe has taught us anything, it's that the line between destruction and creation is thinner than we think. Lurking at the heart of the Virgo cluster, a supergiant elliptical galaxy known as Messier 87 wages a silent cosmic war, one where gravity is the ultimate weapon, and entire galaxies disappear without a trace. This isn't just any galaxy. It's a celestial titan, a gravitational bully swallowing its neighbors whole in a process so relentless astronomers call it galactic cannibalism. Over billions of years, M87 has grown to immense proportions by devouring smaller galaxies, their stars shredded into streams that now orbit like ghostly ribbons in its halo. But the real horror lies at its core, a black hole so massive it tipped the scales at 6.5 billion suns, the very one immortalized in humanity's first ever black hole image. The Event Horizon Telescope's iconic snapshot revealed M87's monster as a fiery ring of light, the silhouette of an event horizon warping spacetime itself. Yet that image only scratches the surface of the violence here. From this black hole's poles erupts one of the most powerful relativistic jets in the known universe, a stream of plasma screaming outward at 99% the speed of light, stretching 5,000 light-years into the void. This jet isn't just spectacular, it's a cosmic particle accelerator flinging matter across intergalactic space with enough energy to outshine entire galaxies. How does a black hole, an object famed for sucking everything in, become the universe's most efficient slingshot? The answer lies in the chaos just outside the event horizon. As M87's black hole feasts on stolen stars and gas, the material doesn't plunge straight in, it spirals into an accretion disk so hot it glows with X-rays. Magnetic fields, twisted by the disk's insane rotation, channel some of that infalling plasma into bipolar jets, funneling it away like water from a cosmic fire hose. These jets aren't smooth streams, they're lumpy, flickering unpredictably, hinting at titanic battles between gravity and magnetism happening in real time. Some theorists believe the key to their power might be the black hole's spin, a rotational energy so vast it acts like a dynamo, turbocharging the jets beyond what mere accretion could explain. But M87's appetite has consequences far beyond its core. The galaxy's sheer size, twice the diameter of the Milky Way with 10 times the stars, comes from a history of collisions written in the skewed orbits of its remaining satellites. Telescopes have caught it red-handed, trails of globular clusters, the skeletal remains of devoured galaxies, orbiting in strange, elongated paths. Some stars even move backward, a telltale sign of past mergers where galaxies came in at odd angles, their trajectories scrambled by M87's overwhelming gravity. This isn't just growth, it's domination, a cosmic ecosystem where one galaxy rules through annihilation. What makes M87 particularly chilling is how common this behavior might be. Elliptical galaxies, the universe's largest, are thought to grow primarily through such mergers, a hierarchical assembly where bigger galaxies consume smaller ones in a cycle that's shaped the cosmos since the first stars ignited. Our own Milky Way is no exception. It's currently digesting the Sagittarius dwarf spheroidal galaxy. But M87 is a glimpse into the far future, a preview of what happens when a galaxy runs out of competitors and stands alone, bloated on the remnants of its rivals. Yet even as M87 feasts, it offers us a gift, a laboratory for extreme physics. Its jet, visible across multiple wavelengths, lets us study how black holes transform matter into energy on scales we could never replicate on Earth. The galaxy's violent history helps us piece together how clusters evolve, how dark matter shapes these collisions, and most profoundly, how even the mightiest structures in the universe are never truly isolated. They're all connected by gravity's invisible threads, locked in a dance that's as beautiful as it is brutal. So the next time you see that famous black hole image, remember, you're not just looking at a singularity. You're seeing the engine of a cosmic predator, one that's still shaping its corner of the universe one meal at a time. Among the countless remnants of dying stars, the Blue Ring Nebula stands apart, a celestial anomaly glowing with ultraviolet light, its twin cones of gas stretching outward like the wings of a cosmic butterfly. Discovered in 2004, this nebula defies classification, caught in a fleeting stage of stellar evolution so rare we've found nothing else like it. The secret to its ethereal glow, a violent merger just a few centuries ago, when two stars locked in a gravitational embrace collided and reshaped themselves into something entirely new. At first glance, the Blue Ring Nebula's name seems misleading. Through optical telescopes, it appears as a faint bluish smudge, but switch to ultraviolet and the truth reveals itself. A double-lobed structure, its cones of hydrogen gas lit up by shock waves from the central star. This isn't just a dying star's farewell, it's the aftermath of a stellar tango gone wrong. The leading theory suggests a sun-like star and a smaller companion spiraled inward over millennia, their orbits decaying until they finally merged in a cataclysmic embrace. The energy released blasted away the outer layers, creating those symmetrical cones, while the surviving core, now spinning wildly from the merger, launched jets of material at breakneck speeds. What makes this nebula so extraordinary is its timing. Most stellar mergers are either too fresh to study a chaotic, dusty mess, or too old their structures faded into the interstellar medium. The Blue Ring Nebula is caught in the sweet spot just long enough after the collision for the debris to settle into a visible pattern, but not so long that the evidence has dissipated. It's like stumbling upon the aftermath of a supernova mere days after the explosion, with the debris still glowing hot and the story fresh. Then there's the mystery of the ring itself. Unlike planetary nebulae, where rings form from slower, steadier stellar winds, the Blue Ring's signature feature likely comes from a shroud of debris material ejected during the merger and later ionized by the central star's intense ultraviolet radiation. This creates a fluorescent halo, a temporary marker of violent stellar history. But here's the catch: this phase won't last. Within a few thousand years, a blink in cosmic terms, the ring will fade, the gas will disperse, and the nebula will vanish, leaving behind only a rejuvenated star spinning furiously from its explosive rebirth. The Blue Ring Nebula challenges our assumptions about how stars live and die. Most stellar deaths are slow, predictable affairs, red giants shedding their layers or white dwarfs fading quietly. But this object reminds us that sometimes stars go out with a bang, rewriting their destinies in a single, violent act, and for astronomers it's a golden opportunity. By studying its light, its structure, and its chemistry, we're glimpsing a process normally hidden by cosmic timescales, a chance to understand how mergers shape the universe, one cataclysm at a time. Perhaps the most poetic lesson lies in the nebula's glow. That eerie blue light isn't just radiation, it's a beacon from the past, a signal from an event that unfolded around the time Galileo first pointed his telescope skyward. In a universe where change often unfolds too slowly to witness, the Blue Ring Nebula is a rare and fleeting gift, a cosmic whisper saying, "Look closely." The universe is stranger than you think. Hidden in the faint constellation Coma Berenices, a ghost haunts the cosmic web, Dragonfly 44, a galaxy that shouldn't exist. From afar, it resembles the Milky Way in size and shape, but peer closer and the illusion shatters. This cosmic phantom emits barely 1% of the starlight our galaxy does, its sparse stars scattered like lonely campfires in an endless night. The chilling truth: Dragonfly 44 is 99.99% dark matter, a shadowy leviathan whose existence rewrites the rules of how galaxies form. The discovery came thanks to a clever trick of physics. In 2016, astronomers studying the Coma cluster noticed something peculiar. This dim galaxy's stars were moving far too fast for its feeble glow. By measuring their velocity dispersion, the slight variations in stellar speeds caused by gravity's tug, they calculated Dragonfly 44's mass. The result was staggering. A Milky Way-sized heavyweight tipping the scales at 1 trillion solar masses, nearly all of it invisible. It's as if someone stretched our galaxy's stars impossibly thin, then replaced everything else with an unfathomable halo of dark matter. What makes Dragonfly 44 so perplexing isn't just its darkness, but its defiance of the missing satellite problem. For decades, simulations predicted swarms of small, dark matter-rich dwarfs orbiting larger galaxies. Instead, we found far fewer than expected, until Dragonfly 44 revealed a twist. What if some missing satellites weren't dwarfs at all, but Milky Way-sized ghosts we'd overlooked? Its existence suggests dark matter galaxies might be hiding in plain sight, camouflaged by their star-starved silhouettes. Then there's the puzzle of its birth. Most ultra-diffuse galaxies form in quiet cosmic backwaters, but Dragonfly 44 lives in the crowded Coma cluster, where gravitational tides should have torn its fragile stellar population apart. How did it survive? One theory posits its dark matter halo acts like an invisible shield, dense enough to protect its few stars from cluster chaos. Another idea suggests it's a failed galaxy, a primordial cloud that gathered dark matter early on but never accumulated enough gas to spark prolific star formation. But the real shock came when researchers studied its globular clusters. These dense stellar swarms, typically tied to a galaxy's luminous mass, were far more numerous than Dragonfly 44's meager starlight could explain. Instead, they aligned with its dark matter mass, hinting that these clusters might trace invisible structure better than stars themselves, a potential roadmap to mapping the unseen. Dragonfly 44 forces us to confront how little we understand about dark matter's role in galactic evolution. Is it a cosmic aberration or the tip of an iceberg, part of a hidden population of shadow galaxies? Future telescopes like the Vera C. Rubin Observatory could unveil more of these phantoms, testing whether Dragonfly 44 is a rarity or a revelation. Either way, its very existence whispers a humbling truth. The universe is far stranger than the stars let on. Of all the cosmic mysteries we've uncovered, few have sparked as much debate or as much wild speculation as KIC 8462852, better known as Tabby's star. Nestled in the constellation Cygnus, this unassuming flicker of light became an overnight sensation in 2015 when astronomers noticed its bizarre behavior. Unlike ordinary stars which dim in predictable, rhythmic patterns when planets pass by, Tabby's star flickers erratically, plunging in brightness by up to 22% at irregular intervals. Imagine a light bulb that doesn't just flicker, but sometimes nearly vanishes and no one can figure out why. Initial theories ranged from the mundane to the extraordinary. Could it be a swarm of comets, a passing dust cloud, or, as some dared to suggest, the handiwork of an alien megastructure, a Dyson swarm of energy harvesting satellites orbiting the star? The latter idea, though sensational, wasn't entirely baseless. The star's light curves defied natural explanations, and for a brief moment it seemed humanity might have stumbled upon evidence of cosmic neighbors. But science thrives on scrutiny, and as new data poured in, a clearer picture began to emerge. Recent studies point firmly toward dust as the culprit. Observations from the Spitzer and Swift space telescopes reveal the dimming varies across wavelengths more pronounced in ultraviolet than in infrared, a telltale sign of fine particulate matter scattering light. This isn't the signature of solid megastructures, but of something far messier, microscopic debris likely from a shattered planet or a colossal comet family. Even so, the dust theory doesn't explain everything. Tabby's star also exhibits a long-term, century-spanning dimming trend, fading by nearly 15% between the 1890s and today. No known dust cloud behaves quite like that. The mystery deepens when you consider the star's erratic brightening episodes. In 2017, Tabby's star suddenly flared, becoming 3% brighter over just 48 hours, a spike that natural dust models struggle to account for. Some researchers propose a two-stage scenario, an ancient cataclysm like a planet collision, left behind a vast debris field, while ongoing comet storms stir up fresh dust, creating the unpredictable dips. Others wonder if the star itself is volatile, prone to outbursts that toss material into its orbit. Despite the mounting evidence for dust, the megastructure hypothesis lingers on the fringe, kept alive by the star's stubborn refusal to fit neatly into any one box. Projects like Breakthrough Listen have trained radio telescopes on Tabby's star, hunting for artificial signals amid the noise. So far, the silence has been deafening, but the absence of evidence isn't evidence of absence. Meanwhile, citizen scientists continue to scour data from missions like TESS, watching for new dips that might reveal fresh clues. What makes Tabby's star so compelling isn't just the unanswered questions, but what it represents, a test case for how we confront the unknown. In an era when new telescopes like JWST and the Vera C. Rubin Observatory promise to uncover countless more anomalies, this star reminds us that the universe delights in defying expectations. Whether the final answer is dust, something stranger, or a mix of both, one thing's certain: Tabby's star isn't done surprising us yet. If the Red Rectangle Nebula is a cosmic masterpiece of sharp angles and nested rungs, its celestial cousin, the Red Square Nebula, takes geometric perfection to an even more hypnotic level. Located 5,000 light-years away in the constellation Serpens, this glowing ember in the night sky presents something almost uncanny. A near-perfect square of crimson light, its corners crisp as if drawn by a celestial architect. At its heart lies MWC 922, a hot, massive star in its death throes, ejecting material in spherical waves. So how does a dying star, shedding gas equally in all directions, create something so starkly angular? The answer lies in the delicate interplay of physics and perspective, where dust becomes the universe's straightedge. Unlike the red rectangle's X-shape sculpted by binary star dynamics, the red square's symmetry emerges from a simpler yet equally mesmerizing process. As MWC 922 expels its outer layers, the material doesn't flow outward in a smooth sphere. Instead, it collides with two thick, cone-shaped dust clouds flanking the star relics from an earlier phase of mass loss. These cones act like cosmic stencils, channeling the star's spherical winds into a diamond-shaped outflow. But here's the twist: we're viewing this structure almost precisely edge-on. The angle transforms the diamond into a square, its sides appearing perfectly straight due to the way light scatters along the dust walls. It's akin to shining a flashlight through a prism. The geometry of the object and our vantage point conspire to create an illusion of impossible precision. What makes the red square even more extraordinary is the fine structure within its glowing walls. High-resolution images reveal a series of concentric squares like nested frames in a celestial painting. These aren't just artifacts of light, they're snapshots of the star's episodic outbursts, each layer representing a pulse of material ejected thousands of years apart. The regularity of these shells suggests the star didn't die in a chaotic frenzy, but in rhythmic tantrums, as if its final breaths were timed to some cosmic metronome. Yet the nebula's most baffling feature might be its corners. In nature, right angles are vanishingly rare. Gravity and turbulence tend to smooth everything into curves. But the red square's 90-degree edges persist, defying expectations. The secret likely lies in the dust's microscopic properties. Particles aligned by magnetic fields or radiation pressure could create sharp boundaries where light scatters preferentially, enhancing the illusion of geometric perfection. Some researchers even speculate about the role of photodissociation regions, zones where ultraviolet light from the star breaks apart molecules, creating layered chemical reactions that might paint the nebula's edges with unnatural clarity. Contrasting the red square with the red rectangle reveals the diversity of cosmic artistry. Both are products of stellar death, yet their symmetries arise from entirely different processes, one shaped by binary star dynamics, the other by the marriage of spherical winds and fortuitous viewing angles. Together, they challenge our assumptions about chaos in the universe, proving that even in the turbulence of dying stars, nature finds ways to craft geometry worthy of a mathematician's dreams. And perhaps that's the most profound lesson. The cosmos doesn't just create beauty by accident. Sometimes it uses physics like a sculptor's chisel, carving order from the brink of chaos. In a universe where dark matter is supposed to be the invisible scaffolding holding galaxies together, NGC 1052DF2 stands as a cosmic heretic, a galaxy that dares to exist without it. Discovered in 2018, this faint smudge of stars in the constellation Cetus defies one of astronomy's most foundational rules, that galaxies are ensnared in vast halos of dark matter, their visible stars merely the glittering tip of an unseen iceberg. Yet here, in this unassuming patch of sky, the stars move sluggishly, their orbits too slow to account for anything but the meager gravity of the stars themselves. It's as if someone peeled away the universe's shadowy skeleton, leaving behind a ghostly shell that shouldn't be able to stand on its own. The discovery sent shockwaves through astrophysics, not just because of what it implies about dark matter, but because of the measurement puzzle it presents. To calculate a galaxy's dark matter content, astronomers typically compare its total mass inferred from the motion of stars or globular clusters to its visible mass. In NGC 1052DF2, the numbers simply don't add up. The 10 globular clusters orbiting this ultra-diffuse galaxy drift lazily, their speed suggesting a mass barely exceeding the stars alone. No hidden bulk, no mysterious gravitational pull, just starlight and silence where dark matter's whisper should be deafening. Skeptics were quick to pounce. Could this be an error in distance measurement? If the galaxy were closer than assumed, its motions would require less unseen mass. Early follow-up studies seemed to support this until meticulous Hubble Space Telescope observations confirmed the original distance, 18.7 million light-years, with razor precision. Others wondered if tidal forces from neighboring galaxies had stripped away NGC 1052DF2's dark matter like a thief in the night. Yet the galaxy shows no signs of disruption, its delicate structure intact. Even more puzzling, its sibling NGC 1052DF4 also appears devoid of dark matter, suggesting this isn't a fluke but a pattern begging for explanation. The implications are profound. If dark matter can be absent, does that mean it's not fundamental to galaxy formation after all? Or could this be evidence of something even stranger, like interactions between dark matter and normal matter we don't yet understand? One radical theory proposes that DF2's dark matter was scoured away by ancient galactic encounters, leaving behind a baryon-only artifact. Another suggests it might have formed in a rare cosmic backwater where gas collapsed directly into stars without a dark matter framework, a process thought impossible in standard models. Then there's the elephant in the room. What if dark matter isn't the answer at all? A handful of theorists see DF2 as a nail in the coffin for modified gravity theories like MUND, which seek to explain galactic motions without invoking unseen matter. Yet even MUND struggles to account for the galaxy's motion cleanly, leaving both camps scrambling for answers. What makes NGC 1052DF2 so riveting isn't just the mystery, it's the opportunity. By studying its stars, its clusters, and its environment, we're stress-testing cosmology itself. Whether this galaxy proves to be an outlier or a signpost to new physics, it reminds us that the universe reserves its boldest lessons for the moments we think we've figured it out. And sometimes the most illuminating discoveries aren't the ones that fit our theories, but the ones that shatter them. Somewhere in the vast intergalactic void, a cosmic fugitive is making its escape. A supermassive black hole 20 million times heavier than our Sun, blazing through space at 4 million miles per hour and leaving behind a contrail of newborn stars stretching 200,000 light-years. This isn't just a wandering giant, it's a gravitational outlaw, and the story of how it broke free reads like the most dramatic prison break in cosmic history. The scene of the crime lies 7.5 billion light-years away, where astronomers first spotted the telltale streak of bright young stars using NASA's Hubble Space Telescope. At one end of this stellar wake sits the black hole itself, a dark engine plowing through intergalactic gas so violently that it triggers star formation in its wake. Behind it glows an almost impossibly long river of blue stars, too young, too hot, and too perfectly aligned to be anything but the aftermath of something extraordinary. The leading theory, a catastrophic three-way galactic collision that turned the orderly dance of gravity into a cosmic slingshot. Picture this, 3 galaxies, each with its own central black hole, spiraling toward one another in a gravitational tango billions of years ago. As their stars intermingled and their dark matter halos merged, 2 of the black holes paired up in a tight binary system, a fate that should have been temporary. But when the third galaxy's black hole entered the fray, chaos erupted. The trio's gravitational interactions became a game of cosmic pinball, with one black hole getting flung outward at unimaginable speeds while the binary black holes recoiled in the opposite direction. Simulations suggest the ejected black hole didn't leave empty-handed. It carried an entourage of stars along with it, their gravity yanked along for the ride. What makes this runaway black hole truly remarkable isn't just its speed or size, but the accidental masterpiece it's painting across the void. As it barrels through clouds of intergalactic hydrogen, the black hole's immense gravitational pull compresses the gas in front of it, while its motion generates shock waves behind it. These disturbances create perfect nurseries for stars' regions where gas collapses under its own weight, igniting the blue-hot giants that now mark its path. It's as if the black hole is scribbling its signature across the cosmos in starlight, a 200,000-year-long brushstroke of creation born from destruction. But the story doesn't end there. Back at the scene of the collision, the remaining binary black holes might still orbit one another, their dance gradually decaying as they lose energy to gravitational waves. Future observations could reveal their presence through periodic ripples in starlight or X-ray flares as they consume nearby matter. Meanwhile, the runaway continues its lonely journey, destined to drift between galaxies for eternity, a cosmic castaway with nothing but its stellar wake to tell the tale. This discovery forces us to rethink how galaxies and their black holes evolve. If such violent ejections are common, there could be countless rogue black holes threading the cosmic web, invisible except for the stars they birth along the way. Some might even be closer than we think, lurking in our own galactic neighborhood, their trails hidden by dust or distance. What's certain is that the universe has a flair for turning chaos into beauty, and this runaway giant is proof that even the darkest objects can leave behind the brightest legacies. The universe should be teeming with civilizations at least, that's what the math suggests. With billions of galaxies, each hosting billions of stars, the cosmic census ought to be crowded with voices. Yet when we listen, all we hear is silence. This eerie absence is the heart of the Fermi paradox, and lurking within it is a terrifying possibility. The Great Filter, a cosmic-scale structure of annihilation so potent it wipes out civilizations before they can ever meet. Whether it's a relic of the past or a looming future threat, this unseen barrier might be the reason the universe feels so empty. One unsettling idea is that the filter already lies behind us, an evolutionary gauntlet so improbable that Earth's survival was a fluke. Consider the razor's edge of our own history. Life emerged early on a planet with just the right ingredients, shielded by a stable star and a protective magnetic field. But then came the oxygen catastrophe, snowball Earth, asteroid impacts, each a potential dead end. The leap from single-celled organisms to complex life took billions of years, hinting at some bottleneck so severe that microbial life might be common, but multicellular existence vanishingly rare. Even the rise of intelligence isn't guaranteed. For 99% of Earth's history, nothing like humans existed. If any of these steps were statistical miracles, we might be among the universe's lone survivors, staring into the void with no one to answer back. But what if the filter isn't behind us but ahead? The same technology that lets us reach for the stars also carries the seeds of our undoing. Nuclear war, runaway AI, bioengineered plagues, humanity's greatest innovations could become the tools of self-destruction. Climate collapse looms as a test of collective intelligence, one that past civilizations might have failed. Even something as seemingly benign as social media fracturing global cooperation could stall progress indefinitely. And then there's the silent killer, complacency. A civilization that retreats into virtual worlds or loses the drive to explore might stagnate, its light never reaching beyond its home system. The scariest version of the filter isn't a single event but a cascade. Imagine a civilization that unlocks atomic energy before developing global governance, or creates AI before understanding ethics. Each advancement without wisdom could be a step toward a cliff. Some theorists suggest the filter might even be a cosmic inevitability, like the dark energy that will someday rip all galaxies apart. But for civilizations, some invisible law of physics that makes collapse unavoidable past a certain threshold. Yet there's a sliver of hope. If the Great Filter is behind us, we've already beaten the odds and the cosmos might be ours to explore. If it lies ahead, recognizing its shape could help us navigate it. That's the paradox's gift. It forces us to confront what it means to survive. The silence of the universe isn't just a puzzle, it's a warning and perhaps a challenge. Every choice we make now might determine whether we become another statistic in the filter's ledger, or proof that someone somewhere can slip past it. At the heart of modern cosmology lies a paradox so profound it threatens to unravel our understanding of cosmic evolution. The Hubble tension. On the surface, it's a simple discrepancy. two of our most trusted methods for measuring the universe's expansion rate disagree by a stubborn 7%. One approach, using the cosmic microwave background as a snapshot of the infant universe, suggests an expansion rate of about 67 kilometers per second per megaparsec. The other, based on the flicker of nearby stars and supernova, insists it's closer to 73. 7% might sound trivial, but in a field where precision is measured in decimal places, this gap screams that something fundamental is missing from our equations. What makes this conflict so electrifying is what it implies about the scaffolding of reality. For decades, the lambda-cold dark matter model, our gold standard for cosmic structure, has painted a universe governed by dark energy's push and dark matter's pull. But the Hubble tension suggests cracks in this framework, hinting at forces or structures we've yet to imagine. Could unknown cosmic megastructures be warping spacetime on scales we've barely probed? Or is dark energy itself evolving, changing strength across cosmic time in ways our models don't account for? One radical possibility involves early dark energy, a transient force that briefly dominated the universe's expansion moments after the Big Bang, altering the initial conditions that birthed today's cosmic microwave background. If confirmed, this would mean our most pristine snapshot of the early universe carries fingerprints of a ghostly presence, one that tweaked the cosmos' expansion before vanishing without a trace. Others propose more exotic explanations: primordial magnetic fields threading through space, unseen dimensions leaking gravity into our own, or even a flaw in Einstein's relativity that only manifests across billions of light years. Then there's the structural angle. Could colossal, undiscovered voids or filaments, cosmic underdensities or overdensities spanning billions of light years, be skewing our local measurements? Our Milky Way might reside in a relative bubble of space, its unusual environment distorting our view of the broader universe's expansion. It's like trying to measure ocean currents while floating in an eddy. Without recognizing the whirlpool's pull, we might mistake its motion for the sea's true flow. The Hubble tension isn't just academic nitpicking, it's a potential portal to new physics. Future telescopes like the Vera C, Rubin Observatory and ESA's Euclid mission will map the universe's expansion with unprecedented precision, hunting for anomalies that might tip the scales toward one explanation. Until then, this cosmic riddle stands as a humbling reminder. The universe doesn't owe us consistency. Every discrepancy is an invitation to look deeper, to question harder, and to embrace the thrilling possibility that our grandest theories might be just the preface to a far stranger story. From the Great Attractor's invisible pull to the geometric perfection of the Red Square Nebula, these 25 cosmic oddities aren't just anomalies, they're neon signs flashing at the edges of human comprehension. Each one defies a different assumption, whether it's the Sloan Great Wall mocking the uniformity of space, the diamond planet rewriting stellar life cycles, or the dark flow hinting at realms beyond our horizon. Together, they form a chorus of cosmic dissent singing the same refrain. The universe is far stranger, far more inventive than our textbooks dared to suggest. What binds these enigmas isn't just their defiance of expectations, but the way they expose the limits of our tools and theories. The Hubble tension and the Axis of Evil reveal cracks in cosmology's foundation, while structures like the Boötes Void and Dragonfly 44 force us to confront how little we grasp about dark matter's role. Even seemingly artistic flourishes, Hoag's object's perfect ring, Saturn's hexagon, turn out to be masterclasses in physics, proving that nature's creativity operates on scales we're only beginning to perceive. Yet for all their mystery, these structures share a deeper truth, their invitations. Every unexplained alignment, every gravitational paradox is a chance to rethink the universe's blueprint. The Fermi Bubbles and the runaway black hole remind us that discovery isn't just about answering questions, it's about learning to ask better ones. And as we stand on the shoulders of giants like Hubble and Planck, we're reminded that today's impossibilities might be tomorrow's breakthroughs. So here's to the cosmic rule breakers, the voids, the walls, the inexplicable flows. They don't just challenge science, they reignite wonder, and that's where we turn to you. Which of these 25 structures leaves you staring at the night sky with equal parts awe and bewilderment? Is it the chilling silence of Tabby's star or the Great Attractor's unseen hand? Drop your pick in the comments, because the universe's greatest gift isn't just the mysteries we've uncovered, it's the ones still waiting just